All right, okay, so let's get started. I hope that if you were working on iteration 2 yesterday, that you are or were able to successfully deliver what you planned to deliver, although nobody ever is able to deliver what they plan to deliver in that course, and that's okay. That's part of the process, right? That's supposed to be what the process is. Welcome back to Comp 3430 Operating Systems. Today, what I want to be able to do is I want to keep on going with some of the stuff that we were doing yesterday. So the two first learning outcomes here are identify the critical sections requiring mutually exclusive access to a piece of code that will run concurrently using threads or processes, and write code that uses pthread mutex lock to protect a critical section. We're focusing on threads specifically for the first one, but as I mentioned last class yesterday, it's possible for this to happen with processes. And I can show you an example later, but we really want to focus our efforts on threads here. I put tick marks beside these already because we kind of did this already. We did this, but the examples that we were looking at yesterday were kind of like the really basic plus operations. And my goal for today is to do the same kind of thing, but with a data structure, an actual data structure, and making changes to a data structure or using a data structure in a multi-threaded way. After we take a look at those, what I want to do is switch over to thinking about the kinds of bugs that we can encounter when we are using multi-threaded code and locks. Our textbook describes the specific one that we're looking at here, Deadlock, as like, I don't know how they did this study, but they say that this accounts for about 3% of the kinds of concurrency bugs that you can encounter when you're dealing with concurrency. But this is the one that is the most studied in academia. This is the problem that is like the most academic problem, but it's also the most frustrating problem to encounter because kind of like what we saw with pipes, the outcome is just we have code that just gets stuck for non-obvious reasons. And so I want to be able to take a look at this formally. I want to think about what we need to have for Deadlock to be possible. And I want us to be able to think about how we might change code that can deadlock so that it guaranteed does not deadlock. Before we get into any of that, though, I posted this to the discussion forum in the off-topic section, but I thought it was super cool, and I just feel compelled to show it to you. This is an article that's written by someone named Joshua, and the part that caught my attention immediately was this statement in the blog post. And I'll let you read this on your own, but I wanted to bring this video up, and the idea here is that we're doing multi-threading with an emulator and Super Mario Bros. And it's a little frustrating that there's no sound to this, so I came prepared for that too. It would have been really jarring if the sound actually like did what was happening on the screen. Okay, I'm gonna stop the sound. I think this is awesome. This blew my mind when I saw it because it's like, this is threads. This is actually threads. This is what threads are. This is what context switching is. So at the top left side of the screen, this part here, there's scheduler here, and I'm gonna contest that this is actually a scheduler. It's not really a scheduler. This is more the interrupt is happening in this amount of time. And then there are 3 different threads of execution here. And so what this person has done is basically saved the state of the emulator at a certain point when it's interrupted, and then it switches to a different save state of the emulator as it's scheduling another task or another thread here. And then it interrupts and switches to a previous save state, and then it interrupts and switches to another save state. And so it's kind of like keeping track of what the process is doing or what the emulator is doing at each time. And at first I was kind of like, no, this is not multi-threading. This is just Mario and an emulator. But if we think about what an emulator is actually doing for a console like the Nintendo, the emulator is simulating the CPU. That's the job that it's doing. It's simulating the CPU. And an emulator save state in this case is literally the context of the CPU. There are more chips involved in Nintendo that will, affect what we think of as the state. So there's like a separate graphics processor on the Nintendo. But the idea of like switching between these threads is effectively what we're doing with actual multi-threading here. So taking the save state and then putting a different save state on the CPU and just letting it run again. There's other stuff in here, like there's mutexes. So there's actually locks in this where when you enter the underground part of the first level here, only one thread of execution is allowed to enter that lower ground part. So if someone else tries, they get blocked. And the other part was the condition variable at the end. And we'll talk about condition variables on Monday. But the condition variable here is everybody gets blocked waiting at that last part until all of the different states are arriving at that last part. And yeah, like I said, this blew my mind as I'm watching this. There's no way that this is threads. And then like, yeah, actually, this actually is what threads are. This is what threads are. And I thought that was amazing. So I've put a link to this up on the course webpage if you want to take a look at what is written here, because there's a lot written here about what's going on. And it also describes how the author here did this with an emulator. I don't know what language they're using for this. It's not Python or anything. It's some kind of scripting language, but it explains how they accomplish this task. And I think that's cool. So if you want to take a look at this, I put a link up on the course webpage under the off-topic discussion forum. With that, let's actually talk about threads, and let's actually talk about critical sections. So a very quick reminder here. Critical sections is a block of code. A critical section is a block of code that contains a race condition. And a race condition is really specifically, or more generally, where we have two concurrent things trying to read and update the same thing at the same time with air quotes and literally at the same time if we have multiple cores of execution here. What I want to do today is I want to take a look at the list examples that we've got in this repository. So if you want to follow along with today's exercises, if you want to bring this up on a bigger screen in front of you so that you can take a look at what we're looking at, it's up in the thread management repository, and I've linked to this on the course webpage for today. And I also would like to edit some of these to try and add some mutex locks to that to prevent mutual exclusion here. So I'm going to pop over to my terminal. And the first example that I want to take a look at today is list traversal a.c. The idea is that I'm going to ask you the same question here. Ultimately, we're going to step through this code, and I'm going to ask you whether or not this code contains a critical section. Just quick thumbs up, thumbs down. And then we'll try and protect the critical section with locks if it's necessary for us to do that. So this is our first, and this is kind of a more basic example with list structures. What we've got here is a node type. It's a very, very basic linked list. This is just going to be something that has a string in it and then a pointer to next. Our list is kind of rooted here with this head node reference that we've got at the file scope variable. So all of the things that we're going to be creating are going to be working with this head node. The operation that we're doing with this code is we're doing traversal of our list. So traversal here is I'm going to start at the head node. I'm going to print out the node that I'm currently looking at, move to the next node, check to see if it's not null, check to see if it's not the end of the list, print out the value, move to the next node, and kind of keep going until we get to the point of null being encountered, the end of our list is encountered, and then we'll stop. In the main function, we're calling a function that's called build list. Build list is being executed entirely by the main thread of execution. So this is not concurrent. We're not building the list concurrently. This is all going to happen within one thread of execution. So the build list function I put below here because we don't really need to think about this in terms of critical sections of our code. We are going to create two threads of execution. And they're both going to be doing thread traversal here. And our main thread of execution is then going to wait for these threads to finish. The build list function, all it does is build up a list that has 101 nodes in it. We have a head node, and then we build nodes counting up to 100 after this. I'm going to open up a new terminal. And I'm going to make this just in case there are changes from last time. There are not. I'm going to run thread traversal, list traversal A. I'm going to scroll up here a little bit. And I'm going to focus on thread traverse here. I'm going to run this once more. And I'll give you a moment to think about this, but I'm highlighting this section of the code specifically. My question is ultimately going to be, does this piece of code have a critical section in it? So no thumbs up yet, just think about it. Okay, so thumbs up says, yes, there's a critical section in this code. Thumbs down says, no, there's no critical section in this code. Everybody, thumbs up, thumbs down, decides. Everybody, thumbs up, thumbs down. Everybody, thumbs up, thumbs down, decides. Okay. So I'm seeing many thumbs down, some thumbs up. There is no critical section in this code. There's no race condition in this code. The output, you might have noticed, looks a little weird. There's output here that's like hello world at the very, kind of in the middle of the screen here, and then hello world again at the bottom. We have two threads of execution that are iterating over this list and printing things out. They're both printing to the same standard output. But in terms of the actual act of iterating over this list, there's no critical section here. The list object there is shared. This is shared data between these two threads of execution. But the part that we're actually updating, the thing we are actually updating in our thread of execution is a thread local value here. So head is shared among both threads, but cur is thread local. And because cur is the only thing that we're updating here, we're taking the value of cur's next and we're setting that to be cur. We're not going to have a situation where our two threads are going to be trying to update the same memory location. So cur is thread local here. Another really quick kind of way to say there's probably no critical section in this code is we're not updating anything. We're not actually making any changes to the data structure that we have here. This is not a universal truth, but one quick way to say that there's probably not a critical section is there are no changes being made to this structure, so I don't really have to worry about that. Does that make sense to everybody? Any questions? We're good? Okay, awesome. The next one I want to look at is list traversal B. List traversal B, I'm going to scroll down to main. It's exactly the same, what we were doing in main. Build list is the same function. We're not adding anything new here. I'm going to pop up here, and I'm going to give you just a moment to take a look at what's on the screen right now. And I'm going to ask that same question. So just hold for a moment. Okay, so quick thumbs up means yes, there's a critical section. Thumbs down means no, there's no critical section in this code. All right, yeah, yes, there is definitely a critical section in this code. This code, when I run list traversal B, will often segfault when I run it. This will often or always segfault when I run it. And the critical section in this code is really specifically on line cur is equal to cur next here. The change that was made between these two examples is that cur itself is now shared between the two threads of execution. We're still not updating the list. We're still not making any changes to the list itself, but the value that we are making changes to, cur in this case, this is shared between the two threads of execution. This is not an atomic operation. This is a load and a store. There are two instructions for this. I have to load the next for cur, and I might even have to load cur itself first. I might have to do two or three separate load operations to be able to do this. To load the value for cur, I have to load cur's next, and then I have to store that value in what cur is. So this line here, this isn't even plus plus, and it's still not an atomic operation. So we've got this critical section and the situation that we're going to be in here, and I'm just going to verbalize this as opposed to draw it out. We're going to draw another example with this, but I'm going to verbalize this idea. If we have two threads of execution, we might be in a situation that one thread is going to get a value for cur next here after it's done the test for cur is not equal to null. So thread 1 gets that, and then it's interrupted. Thread 2 will also get cur next, and that will set cur to null. So then when I go to test to see if cur is not equal to null on the next iteration, thread 1 is going to have null here when I try to do this line again. So I'm going to print this out, and then I'm going to get cur next in the next thing. And then I'm going to dereference this, and it's going to be trying to dereference null. Ultimately, we're going to get into a state where one thread sets it to null, and the other one is already inside the loop before it's been able to do that. So in a lot of cases, or in every case, this code is expected because of the critical section that we have here to result in a segmentation fault. We're going to wind up in the situation where one thread has set this to null without the other one knowing. Yeah?
It seems like all the examples where there is critical sections have to do with shared global variables. Is there not other cases where you could have shared variables?
So all of our examples so far with critical sections and race conditions specifically have to do with shared state, yes. And that's key to this idea. If we don't share state, then we don't have a critical section. So the last example, we were sharing state with our list itself, but we weren't sharing our local state. We weren't making changes to the list, and we weren't sharing our local state. In this case, we're sharing our local state across two different threads of execution. So I guess the answer is it kind of depends on what's happening to the data structures or what's happening to the shared thing that you're operating on or using. If you're just using it and you're maintaining your own pointers to local state, then you don't have a critical section. If you are just reading it, but you are sharing your local state with somebody else, then you might have a critical section. Any other questions about this one? We're good? Okay, awesome. The last one that I want to share with you is listinsertion.c. Listinsertion.c is going to go through the process of initializing a list. And then our task is going to be that I want to have a multi-threaded or concurrent construction of the list ultimately. So I'm going to go down to the main function first here. In our main function, what I'm doing is declaring some number of threads. So in the starting case here, I've got 10 threads of execution that I'm ultimately going to launch for this. I am also going to insert threads of I'm going to insert nodes to this list using threads of execution by passing them the operation that I want them to apply. So this node insert structure, and I'm going to go up to that node insert structure just for a moment here, says I want to insert after this node in the thing that you've been passing to me, and this is the thing that I actually want to insert. So insert after is a node that's in the list already. To insert is something that is not yet in the list, but I want to take this and I want to make this node's next be equal to this ultimately. But I want to insert it so that I'm not losing the rest of the list. If that node already points at something, I want to make sure that I'm just going to insert it in the middle of the list here. So each thread of execution is going to get its own insert after operation, node insert operation. I'm going to build the list, and my build list function here is quite a lot simpler. I'm just allocating a head, so there's only one node in this list when it starts. The print list function prints the list. It will print the list. It iterates over the list. Build list and print list are not going to be executed concurrently. They will be done only by the main thread of execution. The main function and the main thread of execution creates as many insert operations as there are threads. Then we launch all the threads, then we wait for all the threads, and then we print out the list after we've done this operation. I'm going to go up here. This is the function that's going to be executed concurrently, thread insert after. It's a little wide, so I'm going to zoom in here. I'm going to give you a moment to take a look at this, to think about it. And I'm going to ask you the same question ultimately, whether or not this code contains a critical section. And I'll give you a moment. Okay, I'll give you 5 more seconds to furrow your brows at this code. Yeah. And then I'll just ask for kind of a gut reaction at this point, unless you have a solid idea. Okay, so thumbs up, this does have a critical section. Thumbs down, this does not have a critical section. And I will allow people to do thumbs sideways for I'm not quite sure. Okay, so lots of I don't really know for sure. Okay, I'm going to run this code. So this is called list insertion. And what I would expect with list insertion is that when I'm making 10 threads of execution here, I'm making 10 additional nodes, and this list has one node to start. So if I cause 10 threads to start, I'd expect 10 additional nodes to be inserted into this list, and then I'd have 11 total nodes in the list. And we're going to be able to see that when this, this final print statement prints out. It summarizes how many nodes are in the list. And it looks good. It looks okay. It even looks like it's printing it in an order that I kind of expected it to print in here. Hello was the first head node, and then we're always inserting just after the head node. So the 0th thing that was inserted got inserted to effectively the tail, because that was the first thing that got inserted here. I'm going to go back over here, and I'm going to change the number of threads to 100. Same thing, there's one node to start. The head is the first node. And if I launch 100 threads, I'd expect 100 additional nodes to be inserted into this list. So I'd expect there to be 101 total nodes in this list. Looks good. I'm going to do 1,000 threads of execution now. I'm going to make it, and I'm going to run it. I'm going to make this 10,000 threads. I'm going to make it, and I'm going to run it. It's becoming more obvious that this is happening now. I'm going to make this 100,000 threads. I'm going to make it, and I'm going to run it. We just lost 23 nodes. We just lost 23 nodes. Let's take a look at what's happening here. This function is being executed concurrently. So there's one or more threads that are executing this at the same time. I'm going to start to draw a picture here that's describing what's happening in the state where we're losing threads. The best case here is obviously the nodes, sorry, we're losing nodes. The best case is that we don't lose any nodes, and we could see that we weren't losing any nodes with just a very small number of threads of execution. But as we increase the number of threads of execution, we're getting into a state where we're kind of losing stuff. We appear to be losing things. So I'm going to contrive this with 2 threads of execution. I'm going to have thread 1, and I'm going to have thread 2. Both of these threads are going to be assigned an insert operation. Both of them have an insert after and a to insert. In all cases, insert after, I'm going to pop back to the code here for a second, and I'm going to scroll down. In all cases, insert after is head. So we're always inserting it to position number 1 in this list. So right after the head node is where we're going to put this thing. So if my list starts initially as head with no other nodes in it, thread 1's insert after is head, and thread 2's insert after is head. The first step is that thread 1 is going to get to go, and I'm going to say that thread 1 has a node n1. So this is the new thing that it's going to insert into this list. The very first operation, I'm going to switch back to my code here. The very first operation that this does is it takes insert afters next, and it sets 2 inserts next to be that value. So I'm going to take n1 here, and I'm going to duplicate what head.next is. I'm pointing to the tail of the list. And at this point, I'm going to say that I'm interrupted. Thread 1, its execution is interrupted. So now thread 2 is going to take over. Thread 2 has a node n2. It's going to do the same operation. It's going to say n2's next is equal to insert after's next. But then it's going to complete its operation. I'm going to say that thread 2 gets to complete operating in this function, and it will return from the function. The next line says that I'm going to change insert afters next to be this node. So thread 2 has succeeded in inserting its node. Thread 1 got interrupted in the middle of this operation. Thread 1 now gets to finish. The second line of our code in this function says, I'm going to take insert afters next and set it to be to insert. Thread 1 is going to get to go again, and it's going to delete that, and it's going to say that insert afters next is this. Node 2 is still there. It's still in memory. It still points at null. but nobody's pointing at it. We can't reach that node in the list. We cannot reach that node in the list. It's still there, we've leaked it. It's pointing into our list somewhere, but we cannot reach that node in the list anymore. We okay with that? Okay. This is obviously the worst case scenario, where we have one thread of execution that gets interrupted after doing half of its operation. Most of the time, we're able to see when we run this code, and when we have very small numbers of threads of execution, most of the time it just works. And I'm going to run this a bunch of times, and it just seems to be working every time. And it's only when we get to the point of adding lots and lots of concurrency does it start to show the kinds of problems that we're seeing here. And so the next question is, I don't want to lose nodes. I really don't want to lose nodes. And so we want to start making some changes to this so that we can prevent this situation from happening in the first place. There's a few different places that we can start to think about putting locks. I'm going to make this back up to 100,000 here so that when you pull this repository, you can have the kind of broken state of this so that you can see this happening each time you run it. There's a few different places that we could think about putting locks. The first place that we can think about putting locks here, and I'm not going to write this code, I'm just going to put comments in here to say this is where we might acquire and release a lock in this code to make it work correctly. One place is we could have a file scope lock that we acquire here. And then a file scope lock that we release here. That would fix it. We would never get into a state where one thread of execution is interrupted in the middle and another thread of execution is allowed to proceed with inserting something into this list. The problem with this is that we've serialized it again. If I make this a file scope lock, I might as well just do all these insertions in a loop because each thread is going to have to wait for every other thread to finish before it's allowed to insert the thing that it's supposed to insert. File scope works, but it minimizes concurrency. This is a correct place to put the lock. It results in my data structure being what I want it to be, but the performance now is going to be reduced to effectively just running this in serial, and we don't actually get any benefit of having multiple cores running this all at the same time. The other place that we could put a lock is not in the function itself or at the file scope, but in one of our structures here. I'm going to type this out. We could put a lock in each of these places. If I put a lock in this node insert structure, and I'm going to go down to my main function for a second. The node insert structure here is initialized in my main function. It is a stack allocated variable in my main function, but I'm passing each of these insert operations to the thread that's going to run this function. So every thread of execution is going to get its own copy of an insert operation. So I'm not passing null here as the last argument. And what I'm doing in the function itself is I'm using that args value now, and I'm casting it to the type that I've passed to this thread of execution. So very quick show of thumbs, is this going to work if I put a lock in this operation here? I see 2 thumbs up. One person's not willing to put their thumb all the way up, one in the middle and one down. Okay. We could put a lock here. It's not going to work. This is not going to work. It's not going to be a correct placement of our lock. And I want to think about this for a second. This is not going to work because it's effectively the same as a thread local lock. It's a thread local value. Every thread gets its own insert operation. Each thread of execution has its very own insert operation. And that kind of means that if I put the lock here, every thread just gets its own lock. Nobody's going to hold the lock except for that one thread of execution. And if I am thread 1, I'm just going to get it because I'm the only one that can lock it. And thread 2 is just going to get it because it's the only one that can lock it. And thread 3 is just going to get it because it's the only one that can get it. Every thread gets their own lock. And so everybody's able to acquire the lock immediately without waiting because everybody has their own independent lock at that point. The other place that we could put a lock is in the node structure itself. We could put a lock here that's going to lock or prevent concurrent modification of each node. I could have a lock on head. And if any thread of execution tries to make changes to heads next, then there will be a lock around that. If any thread of execution tries to make a change to thread 50,000s, node 50,000s next, there will be a lock for that node itself. If I put the lock here, this is going to work correctly. This is a correct placement of the lock because every thread of execution will try to lock the node before it makes changes to it. This will maximize concurrency in most cases. The case that we're doing right now, it's not going to maximize concurrency at all. It's going to be the same as serializing it because we're always inserting after head. We're always inserting after head. But in the general case, if you're just arbitrarily inserting into random locations in the list with this, then we're going to maximize that concurrency. An insertion after head and an insertion just before the tail, if they're very far apart, that will truly happen at the same time, as opposed to having to wait one for the other. So this maximizes concurrency in most cases, but not for this specific contrived example, because we're always inserting after head. Yeah.
Because you created the nodes kind of in your main function, so both threads kind of have access to those shared resources, right? And we're saying that put a lock on like the actual value for the next point of the node, where the node points to the same memory location for 2 different threads, right? So we're just saying that we cannot have 2 or more threads changing that specific memory in the keyboard, the main stack, right?
In the heap in this case, because the nodes themselves have been allocated with malloc. If I go down here, yeah, we can see that's being done. But you got the right idea in general. This is something that's going to be unique per node. And because the node is the thing that we're operating on here, every thread is either going to, if it's operating on the same node, it's going to have to wait for that lock to be released. If it's operating on completely different nodes, then it will be able to get it. If I were to create this to insert up here, it actually wouldn't make a difference If I said malloc in this function, it's more because we're inserting into a node that's already, we're inserting after a node that's already in the list, and the list itself is shared across all nodes. So the problem is more this part of the operation. Whoops, I'm sorry, it's this part of the operation. Insert after is already in the list. It has to be already in the list for us to be able to insert after it. And that part is that state that's shared across all of the threads of execution that we've got. Yeah. Yeah. Well, it depends on how you write your code to use this. In the case that we're talking about right now, I would want to do something like this. pthread mutex t next lock, something like this. I would declare the lock like this. This object could have more than one lock. I could have another one that's pthread mutex t read lock. So if somebody is making changes to what value is here, I don't want them to read it until after I've finished making those changes, if it's a long non-atomic operation that I'm doing to that. But in the case that we're thinking about right now, I'm saying I would have just next lock like this. And then here I would say I want to put a lock pthread mutex lock, and I want to pass to this insert operation insert after next lock, something like that. So I want to make sure that you're not going to make changes to the same node that I am concurrently. Yeah. Well, I'm going to make these two statements become an atomic. If I've got some other function that is printing the list, so if I have something that's iterating over the list, then I may not, but I might want to have it there. It kind of depends. Yeah. Yeah. I'll finish this off. So this will maximize concurrency, but not so much for the example that we've got here, because we're always inserting after the same node every single time for every single thread of execution. All right. Okay. So what I like about this example is that it takes quite a lot of increasing concurrency to actually see this happening. In most cases, In most cases, we're looking at this code and running it, and it's the correct output that we're expecting to see, but it's only after we get to 100,000 threads of execution that we really begin to see the problems showing up with this code. What I want to do now is take a look at a different kind of bug that can happen with concurrency. I said earlier, this bug is kind of it's not the most common kind of bug that happens with concurrency. The kind that we just saw is more likely to happen in general than what we're looking at with Deadlock. But it's the one that is kind of stuck in academics' minds. The outcome of Deadlock is sort of what you might think it is based on its name. You run a piece of code and it just gets stuck. It's not doing anything. It doesn't seem obvious why it's not doing anything, but you're not printing any messages out. You're not making any progress. And if you looked at your resource monitor on your operating system, you would see that the process is just doing nothing. It might be spinning at 100% and doing nothing, but it's just doing nothing. It's not making any progress and it's not getting anywhere. Deadlock is the condition where we have this code that's just stuck. And deadlock happens in concurrent code when all four of these different conditions hold. And when I say hold, I mean to say when it applies to the code that we're looking at. So when this is actually true for the code that we're looking at. The four conditions are mutual exclusion, hold and wait, no preemption, and circular wait. And we'll look at each of these in a moment. What we can say about deadlock with all 4 of these different conditions holding is that it's possible for deadlock to happen. We can't guarantee that deadlock will happen with code. For deadlock to happen, we have to be in a lot of the right circumstances, kind of in the same way that we did have to be with that list insertion example. We've got to be in the right set of circumstances for us to have been interrupted at just the right time for us to enter this state. We can guarantee that deadlock will not happen, but we will happen. We can just say it's possible. Lock the door, you hold the room. Nobody else is going to come into that room. Another example is this. I've got these 2 things that I need to be able to accomplish a task, but we're going to share them. If I give you this pen, you hold that pen. I cannot all person, but I don't want to spend that much time close to you, like holding the pen at the same time. So we're just going to say that it's 1 pen, 1 person. Once you hold it, it's yours. You've got it. To be able to use this tablet, you also need the tablet. You have the pen right now, but you also need this tablet. But I have the tablet right now. I'm holding this. You can't hold it right now because I'm holding it. With hold and wait, threads hold resources allocated to them while waiting for additional resources. Don't put it down. You can put the pen down. While you're waiting for this tablet, not about multitasking. Preemption here is about you've got that pen. Once you hold, do not have it forcibly removing system. Emphatically, it is possible for code to deadlock if all, but we cannot guarantee that it's going to deadlock. However, if any of those conditions are broken, if I can say that no preemption is broken, I'm going to add code that's going to take it away from you if you're holding it for too long. Deadlock cannot happen anymore. If I make it so that we have a circular setup like this, except we've got our pen and our tablet here on the table, and we're going to come up with a rule between us that says if we want to use this thing, I'm always going to get the pen first. I'm not going to try to grab the other one that's free. I'm just always going to get the pen first. If I get the pen first, and you come up here, you don't have to. If you come up here and try to get the pen, it's not there. You can't get it yet. I'm going to get the tablet, and then I'll put them both down, and then you can start taking the pen. If I can make sure that it's not possible for 2 threads of execution or more to be in this state of they're waiting for somebody else to give up something, then I can guarantee that deadlock will not happen. So I want to ask that question, and I'm going to ask you this question in the context of Mentimeter. I'm going to pop this up here, and I'm going to go back. Sorry, forgive me for one moment. I'm going to go back here. We're going to be taking a look at deadlock.c. And I'm going to ask you for each of these 4 conditions of deadlock, does that hold or not hold in the code that we're looking at? This is also in that thread management repository. I will put it up on my screen, but if you want to have a copy of it on your screen, it's up there for you to do that. So I'm going to go back to my terminal here. I'm going to quit, and I'm going to open up deadlock.c. Deadlock.c is in the main folder here. So it's outside of that critical sections folder. And I'm going to describe to you what this code does. I'm going to start way down here at the main function. The overall idea here is that we're managing bank accounts, and we're going to have exactly 2 threads of execution. The operation order here is that lines 82 to 86, these are not concurrently executed. This is only going to be done by the main thread of execution. We're going to make 2 bank accounts, account 1 and account 2. They will have an opening balance of 1,000 units of money, whatever currency you want to use. We'll create 2 different transfer objects. And so now we're following a similar pattern to what we did with list insertion here. We're going to pass these values to the threads of execution. One thread is going to transfer from account 1 to account 2 100 units of currency. The other thread of execution is going to transfer from account 2 to account 1 100 units of 100 units of currency. We're going to launch these two threads of execution to do the two transfers, and the expected result is that everybody has the same amount at the end. I'm transferring from one account and then back to the other account. The main thread of execution will wait for these two to finish, and then it will print out the account balance at the end. The create bank account and the create transfer functions are not interesting because they're not being executed concurrently. The only one that's really interesting here is going to be the deposit function, and it's going to be the accounts themselves. The accounts themselves up here have a balance. It's an integer. We can argue about what's the right type to be using for money. It's not floats, but I'm choosing integers here. And there's a lock. There is a lock that can be held on the account itself if we're going to make changes to the account's balance. Down here in the deposit function, we're accepting an argument this time. So just like that insert operation, we're casting args, which was void pointer to the type that, because I'm writing this code, so I know what type it is that I'm passing to my thread, so I can just blindly cast to this thing. I'm going to acquire a lock on from. So I'm taking money from this account. I want to make sure that if I'm going to take money from this account, that it has enough money in the account for me to take that amount from. So my test here is if I'm transferring 100 units of currency from an account that has 50 units of currency, I'm going to give up my lock and I'm not going to do anything. There's not enough money for me to conduct the transfer, so I'm just going to bail out at this point. If there is enough money, then what I'm going to do is I also want to get a lock on my 2 account. And I want to get locks on both of these accounts because minus equals and plus equals themselves are not atomic operations, but I want the entire transfer to be done atomically. I don't want to be interrupted from one account to another. That's how we wind up with double money or how we wind up losing money. So I want to make sure that this entire transfer is completed before I unlock the locks, release it, and then exit. I'm going to hold this up. I'm going to make this a little bit smaller. I'm going to drag this, and I'm going to pop back to my Mentimeter here. And we're going to step through each of these conditions for deadlock to ask the questions, do each of these hold? So I see lots of people have answered for mutual exclusion. I'll give you 5 more seconds to answer if you haven't answered already. Move it down so you can see the code. Oh, I'm sorry. I'll give you 5 more seconds if you're still getting connected. Okay. So I'm going to take a look at my Mentimeter here now. Most people think that mutual exclusion holds, and I would agree with you on this case. In both interpretations, we are acquiring this lock, and we can guarantee that no other thread of execution is going to be able to work with from's balance after this point, after one is able to acquire it. We can further assume that pthread mutex lock works correctly. It has been implemented correctly, so no one is going to be allowed to enter this section. Similarly, pthread mutex lock on 2, we can guarantee that nobody's going to be able to get past this once one thread of execution has it. So I believe that this has been protected. These 2 lines have been protected adequately with mutual exclusion. Our next condition for deadlock is no preemption. Does no preemption in this code hold? I'll give you 10 seconds to answer. Okay, I'm going to pop over here. It's moving a little bit still, but most people say or think that no preemption holds here. And I'm going to agree with you. There's no place in this code where another thread of execution can forcibly say, give me that lock. There's one place where we're unlocking, but that's not preemption. I'm voluntarily giving up this lock. There's another place where I'm unlocking locks, but this is voluntary. Nobody is taking this from me. I'm the one that holds it right now. I'm volunteering to give it up. We can also further assume that pthread mutex lock does not have preemption. Our operating system does not know about it. The pthreads library doesn't try to take locks away if somebody is holding them. So no preemption in this case definitely holds. How about hold and wait? I'll give you 10 seconds to think about this one. All right. Most people are saying hold and wait is definitely true, and I agree with you. I definitely agree with you. In the code that we've got here, the two key parts are line 44 and line 55 here. Those are the two key parts to hold and wait specifically. Hold and wait here says, I've got a resource, I have a lock, I'm going to hold on to that one while I wait for the next one to show up. It sounded like it might have been an exciting addition to our lecture today. Once I, thread 1, hold the lock on from, and if from has enough money in it to do the transfer, I will wait for 2, and I'm not going to give up my lock on from. Once I have it, I'm going to hold it. This line right here is a little bit of a red herring. It's reasonable for you to look at that and say, well, I'm not going to wait. I'm not going to hold it and wait. I'm going to give it up. And that's true. That is happening. But it's not going to be the case in the other situation where we're actually trying to acquire that lock. Does everybody know what red herring is before I... Has anybody not heard of red herring before? Explain it one more time for that person over there, right? Yeah. A red herring is, it's like from a story. I don't even know what the story is, but it's an idiom in English where it's, I don't know what's going on in this picture, but I love it. It's this idea that like something shows up in a story, but it's a misdirection. Like it's not actually important to the story, but it suddenly looks like it's going to be in this really important thing, which is a different idiom from Chekhov's gun, which is this gun shows up early in the story and then it comes back and it does something important. Red herring here is just something that's just like, but it looks like it might be important to the thing that we're thinking about here. So in this case, what we've got is I am acquiring the lock, and assuming that I get past this point, I will wait for 2 to become available if I already hold from's lock. Okay, here's the next one, and here's the last one. Does there exist a condition in this code where we have circular wait? We've got 2 threads of execution that are running concurrently, and they are each waiting for the other one to give up a resource. I'll give you 5 more seconds, but I noticed that the line here is a little bit more like leaning off to the side in ways that it wasn't for the last 3. All right. Red herring. I'm very sorry. I cannot Alt-Tab today. There does exist a condition where there are 2 threads of execution that are waiting for each other to give something up in this code. From this code alone, it isn't immediately obvious that that's the case. In this code alone, and I'm always going to acquire 2 seconds. It's always in that order. Always from and then to. But the problem that we've got is that when I created this transfer object, I inverted these 2 accounts. And so with thread 1, from is account 1. And with thread 2, from is account 2. And with thread 1, 2 is account 2. And with thread 2, that's super confusing. They're inverted. Similar situation that we've got here. Now I want to try to imagine this for a moment. Thread 1 acquires this lock. It acquires the lock on account 1. T1 gets account 1 lock. And then it's interrupted. T2 gets account 2 lock. It gets to take over. Thread 2 will proceed, and it will get to this point. T2 wants account 1 lock, but it's held by thread 1. T1 gets to take over. T1 wants account 2 lock, but it's held by T2. And so here is my very last question. Can this code deadlock? I'll give you like 3 seconds because the answer is obviously maybe. It's obviously solidly maybe. Okay, yeah, it's solidly maybe. All 4 of our conditions for deadlock hold now. There's a circular wait, there's hold and wait, there's no preemption, and there's mutual exclusion. All 4 of these conditions wait, so it's a very solid maybe. Yeah, maybe this can deadlock. And so I'm going to try in the winter term. I was actually able to make this happen, but it's very unlikely that this code is going to deadlock. And I don't think I want to spend the next 5 minutes trying to get it to deadlock. But I promise I was able to do this twice in the winter term. But then it doesn't, like, it's clearly happened. It actually has clearly happened. Like, Hyperfine is just like, this is going to keep running forever. Yeah, this is a really terrible transfer. But it's actually show it happening by just running it a bunch of times. Notice how the ETA just keeps going up and up and up and up. This is never going to finish. This is deadlocked. One of the executions of this code has deadlocked and it's just stuck. And I really, really want this to happen here. I really do. What? Now I've gone too far. Okay, I'm going to give up. I'm going to give up. I welcome you to try this on your own machine, but we've got one anecdotal report of 25% of the time it deadlocks. And then here I run it 50 times and I've got 0 deadlocks. So I think that we can indeed solidly say that, yeah, maybe this deadlocks. Maybe this deadlocks. And so the question that I'm going to leave us with is, how do we not deadlock? I want to break one of those 4 conditions so that I can guarantee that we will not deadlock. I can confidently say that maybe we will deadlock, but I want to guarantee that we will not deadlock. And so my question for you is, how do we fix it? What could we do to this code to make it so that this code is guaranteed to never deadlock? Get rid of the locks. That is actually a solid suggestion. I know it might be a joke, but it is an absolutely solid suggestion. If I remove the locks, I have broken no preemption. I've broken mutual exclusion. If I get rid of the locks, if I don't try to lock here, if I don't try to lock here, and if I don't try to lock here, we'll never deadlock. We're never going to get stuck in this state where threads are trying to wait for anything else because many of them are just running all at the same time. That breaks what we're trying to accomplish, but we can guarantee that deadlock will not happen. In theory, we could just lock the whole function, absolutely. So I could put pthread mutex t transfer lock here, and I could acquire pthread mutex lock transfer lock here. I could do that. I can lock acquisition, but now transfers are serialized. I can only ever conduct one transfer at a time ever, even across unrelated accounts. And I don't really want that to happen. I want to have multiple threads of execution doing multiple transfers at the same time. Put a deadlock on the account node, put a lock on the account node. There is a lock on the node already on the account object. Up here, there is one on our account object already. Do it all in thread 1. Just do it in one thread. Yeah, I guess that would actually work. Make sure one thread can forcibly use the lock from the other. Yeah, that would work. And so one way, that's not what I wanted to do. One way that we could accomplish this is to use a different function for locking that's called try-lock. It's not really forcibly taking the lock from another one, but it is going to give us the ability to give up the lock if it's not available for us to use. Break the circular wait by making it forced to acquire the same lock first, like in the pen tablet example you said. Yes, this is another good way to do it. Doing this is challenging, though. It's not straightforward how we could accomplish that. I'm going to suggest one way that we could accomplish that. One way that we could accomplish this is by taking a look at from and to here. In our deposit thread args, in this one, looking at the address of these accounts and then sorting them based on the address and multiplying the transfer amount by a -1 to reverse the order of the thing that we're doing. So make sure that the smallest account is always from and the biggest account is always to. And if we do that, then we will enforce this breaking circular wait. This is called total ordering of locks. I'm going to guarantee that lock order acquisition is always the same for everything. I'm going to take a look at a couple of these, more of these. Not relevant, but we can, okay, yeah, you're right. We could have also run this in a loop and we could have made it. The one that I like the best really is this one, break circular wait, by making sure that we're doing the transfers in the order that we're expecting it to be done. So I'm going to I'm going to leave it here for now because we're right at the end of class. But what I will do is on Monday's class, we'll just quickly write this code. It's about 4 lines long to order the accounts to make sure that we always acquire locks in the same order. So thank you all for your suggestions on how to fix this. Which is what we've done here. So awesome. At this point, you should be able to identify critical sections that require mutually exclusive access to a piece of code that will run concurrently using threads or processes. And you should be able to use locks. Again, I want to emphasize that ultimately, pthread mutex lock is a way to do locking, but I think you should be able to use locks generally. Just use this lock ID, a lock keyword, to be able to protect a critical section. You should also at this point be able to identify code protecting a critical section that would result in deadlock and propose solutions that would avoid and or prevent said deadlock. So given a piece of code, you should be able to explain to me how all 4 of the conditions for deadlock either hold or do not hold, and then be able to say one way or the other. Yes, this code does deadlock. Sorry. Yes, solidly, maybe this code deadlocks, but guaranteed, no, it does not deadlock. That's it for today. I hope that you all have a great weekend. And I will see you next week where I will add, there's nothing due in this class. There are no tests. It is just lectures next week. That is it, just lectures.